Everyone. Hello, welcome everyone to this webinar. I'd like to start doing some quick introductions to get going, and then we'll jump into the actual content. So, okay, so welcome everyone. My name is Rob Narenberg. I'm at the University of Notre Dame in the USA, and I'm the chair of the IWA Biofilms Specialist Group. So we're actually the ones that are hosting this webinar. I think many of you, if not most of you, are members of the International Water Association, but I know many may not be. So just a quick overview, the IWA is actually the largest international network of water professionals addressing drinking water, wastewater, research, policy. For those of you from the US, it's like the Water Environment Federation, but global. Within the IWA, there are a number of specialist groups that address different topics. And our group addresses biofilms. So our focus is to have exchange of scientific and technical information among biofilm researchers and practitioners. And we address biofilms, but also the biological, chemical, and physical processes that relate to biofilm behavior. And I guess this webinar, even though it addresses wastewater intensification more broadly, we feel it is a part of biofilms as well. There are a number of, activities that the Biofilm Specialist Group addresses. One of the most important is specialist conferences. So every year or every other year, we have a specialist conference. And I just wanted to let you know the next one is expected to be in 2024 in Shanghai. It hasn't been announced yet, but we hope it'll be announced soon. Also, the IWA every other year has a World Water Congress, and this coming year, 2024, it will be in Toronto. So if you're in North America, heads up, it's an opportunity to attend an IWA conference without having to travel across the world. And we hope to have some biofilm specialist group activity, including a meeting among the specialist group members. And there's at least one proposal for a biofilms related workshop on membrane aerated biofilm reactors. We also hope to have more events like this one. So webinars or other kinds of training and outreach to participants, and even task groups where we can get together to address certain topics. If you're interested in a special topic, or if you'd like to lead a special task group or even a webinar, please let us know. You can email me. Your invitation has my email on it, so it should be easy to respond. We'd love to have everyone's participation. So into today's webinar. So a little bit of history. This webinar was actually started by an idea from Josh Boltz and Sudhir Murthy. And they thought, let's have a workshop on intensification of continuous flow wastewater treatment processes using biological and physical selectors. And this workshop took place in the IWA Biofilms Conference in 2021, which was virtual due to COVID. And I think it was a great success. There were a lot of top-level participants. And after the workshop was over, they continued to meet and they put together a publication. So there's actually a publication from this year, 2023, on the topic that was started at this conference workshop. And now the objective of this conference is to disseminate that information. So again, this has been led by Josh Boltz, who works for Woodward and Curran in the United States. And we have an outstanding cast of speakers that I'll let Josh introduce next. But I wanted to acknowledge Josh's company, Woodward and Curran. There's actually a cost associated with webinars, and his company kindly offered to cover that cost. So I guess this webinar is courtesy of Woodward and Curran. We're very grateful to them for providing that financial help. And with that, I'm done with my presentation, and I'll hand off to Josh.
Okay, thanks, Rob. Okay. Hello to you wherever you are in the world. we appreciate you all joining this webinar. We think this is an exciting and relevant topic. We're going to discuss how biological and physical selectors can be utilized to intensify biological wastewater treatment processes and achieve biological nutrient removal. Again, thank you very much to Woodard and Curran, who provided financial support and sponsorship for this webinar. The format is based on a sequence of brief presentations followed by a discussion and question and answer period. You will be able to watch 6 8-minute presentations by world-class engineers and scientists. Then we will have about 40 minutes for discussion. 291 people registered, which I think shows a great interest in this topic. Our speakers include Glenn Diger from the University of Michigan, Mari Winkler from the University of Washington, Pusker Rejmi from Brown and Caldwell, Bruce Johnson, Jacobs, Clement Roche from Suez, and Keith Sears from AECOM. We strongly encourage you to chat. We encourage active chat throughout this webinar. If you have a question that is directed to a specific person, please identify the person. We will do our best to respond to questions as they arrive in the chat, but if you have a question that is not answered, please know that Jackie Kuo, my co-moderator, will record your question and will address it during the discussion. Be brave, ask questions. There is no poor question. If you don't understand it, it's likely that someone else does not do. And vigorously discuss the matters that we are presenting today. Thank you for attending. And now, our first speaker. Dr. Tiger, please take over.
Okay, so working on getting my presentation up here. And as I do that, let me welcome everybody, extend my welcome. Good morning, good afternoon, good day to all. And my role here is basically to introduce and to frame the discussion that we're looking to have. So I see it says you are screen sharing. I don't see the image up yet. So do others see the image of my slides up yet?
It says end of slideshow.
We did not, and I encountered the same problem. So I simply left the full screen mode, and then tried it again, and it worked.
Okay. So we'll do that here. So give me just a second to work through this. I see. There, that should be a bit better. So can everybody see this?
No, not yet.
Not yet. Keep working on it. We'll get it here.
Okay.
Screen share.
We do see it, but it is not in presentation mode. There
Okay.
you go. You're off.
All right. All right. So again, good morning, good afternoon, good day to all around the world. So again, what I'm going to do is to kind of provide an overview of the complete set of topics that we're going to address here, beginning with why implement the biological and physical selectors in biological treatment systems. So what do they do is to produce and accumulate aerobic granules, densified biological flocs, and mobile biofilms. And In the upper right-hand side, you see a little bit of a photomicrograph that illustrates those. We're going to see more pictures like this as we go forward. So, but the reason we want them, first of all, is they settle faster and compact better than activated sludge flocs. So here you see kind of the classic comparison of settling in a 1 liter graduated cylinder. Because they settle faster and compact better, they allow higher mixed liquor concentrations in bioreactors, so a smaller bioreactor, and higher clarifier solids loading rate, so smaller clarifiers. And who wouldn't want smaller bioreactors and clarifiers or more capacity on what you have? But also, the denser flocs allow redox zones to develop within them, and this is the tie to the biofilms. Essentially, these are biofilms, even though they're in suspended growth systems that we typically don't think about as biofilm systems. And they allow biological nutrient removal without formal anaerobic and anoxic zones. So why wouldn't anyone want all of that? Sludge granulation is accomplished through a combination of biological and physical selection. So biological selection is accomplished by creating alternating feast and famine environments to select for carbon storing organisms that are one of the keys to actually for granules start to develop. We can't have a granular system unless biologically the organisms will tend to granulate. So these organisms produce extracellular polymers, EPS, as is often talked about, using readily degradable organics, or RBCOD is the term we often need, that are needed to produce these dense aggregates. That's the principal role of biological systems. That physical selection selectively retains these dense aggregates and selectively wastes the flocs. So we grow what we want, and then we selectively look to retain what we want. The mechanism for retention are things like hydrocyclone screens and clarifiers. And again, you'll see examples of these as we go through the case histories, but this just is an illustration of the type of equipment that you had. With this, we get different SRTs because we selectively retain the granules, these denser solids. They're actually retained in the system longer than the others. Biological selection depends on both metabolic and kinetic factors. So selectors remove essentially all of the RBCOD and create selective pressure. I'm showing you some information from old literature, going back to old literature, just basically to reinforce that we're building on a lot of existing knowledge. And in the lower example here, you see something that was published quite a long time ago, showing that we have to remove the soluble COD in the selector. If it bleeds through into the main bioreactor, we don't get the improvement in settleability that we're looking for. Now, metabolic selection involves in the selector creating either anoxic, which means the presence of nitrate and the absence of oxygen, or anaerobic conditions, the absence of both oxygen and nitrate. So this is a selective pressure also in terms of the organisms that are created. Kinetic selection, again, comes back to that feast and famine condition. So what you have are small zones at the inlet to the bioreactor. You see that physically, but in the more upper right, these are data from the UK, actually looking at the increased plug flow characteristics in bioreactors expressed by the number of equivalent cells. You see that we need a large number of equivalent cells if this is a strict and plug flow reactor. Full-scale data. What this does, though, is it creates this high organic loading condition that's characterized by the F to M that's needed for selection. And then we select organisms that store RBCOD for later metabolism. They store in the selector, and then they metabolize it in the main aerobic bioreactor. We can characterize this through mass balances. This is a figure from the paper. It's really just an image to show that we are able to characterize the separation of the granules and the flocs and the development of these relative populations. This is well described in the literature, actually by Josh and myself in another paper. So we have the ability to do that. So takeaways from my section here is that, first of all, we have a consistent theory. It's not perfect, but it's consistent in terms of both what we know today, but learning over a long time period that describes how these systems develop and the steps that we need to take to accomplish this. It's advancing with more experience, and part of the purpose of this webinar is to get some of this experience out so others can go out and try it as well. The growing number of full-scale examples, you'll see a few of them as we go forward. An area of further knowledge needed is the relative importance of RBCOD in the production of RBCOD. So this brings us into topics like fermentation and hydrolysis and so forth that we've been working on for decades, but their importance is really highlighted with these systems. We're not going to talk too much about mathematical modeling in the presentations, but our mathematical models are advancing, and they generally incorporate the observed behavior, oftentimes by description, meaning that we input in the model the result that we expect in terms of the proportion and sizes of granules and so forth. So this is an area of further development yet. The biological selection is incorporated in the models. This is an area also of future potential development. So I highlight this for some potential discussion, some topics for discussion. So with that, Josh, I'll turn it back over to you to introduce the next speaker.
Wonderful presentation, Dr. Diger. Thank you. Our next speaker is Dr. Mari Winkler from the University of Washington, who's going to describe the role of biological selection in this form of intensification. Mari?
Yes. Right. Hey everyone, I'm going to introduce the microbiology of large aggregates. My name is Mari. I'm at the University of Washington. So following the presentation of Glenn, the question I'd like to start with is, why do we want large aggregates? And if we look at flocs, they have their small particle sizes, slow settling velocities, a high sludge volume index, and as a result, they thicken very poorly, which leads into large space to separate sludge from the water. And space always is cost as well. Granules and also mobile biofilms, which are very similar in appearance, the difference is that they have carrier material and organic carrier material to grow the biofilm on. Both of these sludge types have high particle size, fast settling velocities, low sludge volume index, and then as a result, they thicken very fast within just some minutes. So following the question why we do want large aggregates, you can see here the aerobic granular sludge that thickens very well, and the activated sludge that doesn't thicken very well, which is kind of a follow-up from the first slide. But there's more to this because there is also some functional advantages. If we look here at a typical continuous flow diagram enabling phosphate removal, denitrification, and nitrification, a little bit what Glenn already explained is that you need separate tanks to enable denitrification and nitrification, and then those space-consuming tanks. In a granule or mobile organic carrier, you will have everything collapsed into just 1 millimeter. And instead of having different tanks, you have aerobic zones on the at the edge where nitrifiers here in red convert ammonium to nitrite and nitrate by these functional groups that grow here in red on the edge. And in the inner core, PAOs and GAOs that can also denitrify grow in the inner part here shown as, this is blue, it looks a little white, the PAOs and the GAOs enabling simultaneous nitrification and denitrification in a very compact manner. So thinking about how do we get large aggregates, I'd like to introduce the concept of what high substrate concentrations or high F2M ratios, again, following Glenn's presentation, will do to granule structure. Well, high substrate concentrations and anaerobic zones form very smooth granules. High substrate concentration and aerobic zones can also lead to storage organisms, but you won't have as smooth granule structures. And as you decrease the substrate concentration in aerobic zones, you get filaments. Granules can allow for simultaneous nitrification, denitrification, and phosphate removal. They require less clarifier or no clarifiers, which leads to less space, and they have high biomass concentrations. And on the far right, you need all the different tanks because you have you need nitrification and denitrification to occur in these different tanks. That also leads to space-consuming tanks to separate the sludge from the water, and that is all due to low biomass concentrations. So following a little bit the thread of how do we get large aggregates, I'd like to look at the microbiology. And it actually gets quickly very complicated, which is why I'm exposing to you to a rather complicated slide that I'm going to break down for you in just a second. Following, again, the first presentation, we have two phases to select for storage organisms, a feast phase and a famine phase. And there's two graphs per phase I'd like to introduce, which is here what happens in the bulk liquid, which is what you measure in the bulk liquid, and also what happens in the cell. And you can see that there's a lot going on in the cell. And what happens in this phase is that you take up the RBCOD, or the volatile fatty acids, in the anaerobic or in the feast phase, and then that is taken up as internally stored PHB. And you can see this here in this graph, which is what happens here. There's these white blobs where the storage organisms, they store the carbon internally, and that will get us to the famine phase, where you can see there's no carbon. So these organisms have all the time they need to oxidize the carbon and do not compete with other heterotrophs. And that leads to this really nice and slow growth, and hence to smooth granule structure. If we now look, if there are granules in continuous flow systems, we first need to look like where granule sludge started, which actually started in sequencing batch reactors that have really high F2M ratios in their anaerobic zone and very short settling times. Conventional activated sludge systems, however, are continuous flow. They can have anaerobic zones and high F2M ratios with the selectors that Glenn introduced. However, there's not really a physical selection, which is posing the question, can we actually get large settling aggregates in continuous flow? Yes, we can. And we have this study that we have done in the past where we looked at multiple EBPR plants that do have that selector and looked at their sludge volume index in comparison to plants that do not have that selector and are not non-EBPR plants. And you can see that the EBPR plants had a very low sludge volume index. And also those that had a low sludge volume index had naturally occurring granules in continuous flow systems, while non-EBPR plants had really poor settling sludge that were floccular. The plants that had low SVIs also had high granule percentage, and the flocs that had high SVIs had low granule percentage. And following the talk, it kind of follows the high F2M storyline that I was telling you. The plants with high granule percentage had high F2M ratios. They typically also had multiple stages, while poor settling sludge with flocs didn't have high F2M ratios and only one stage. Last but not least, the mobile organic carriers shown here have similar microbial population dynamics as shown here. And what you see on this graph is a plant that at first didn't have these carriers in their plant, leading to high SVIs and high TSS, while at the time of the upgrade, both of them really significantly were lowered, leading to a more stable operation. So they also represent a nice way to get large aggregates in continuous flow systems. And that's it. Thank you so much.
Thanks, Maury. Fine presentation. Next, we're going to move to a presentation by Busker Rejmi from Brown and Caldwell, who is going to describe physical selectors. Here.
Thank you, Josh. So let me share the screen. Do you see my screen? Good. All right, so the topic of my presentation is going to be around decoupling of SRT with physical selection. And before I get started with my presentation, I would like to thank a couple of important organizations, Metro Water Recovery, Rudy Maltos, Dr. Rudy Maltos, and Metro staff, Water Research Foundation, the Water Research Foundation 5130 project. Some of the results that I'll be presenting today is part of that project that we are doing at the moment. And with that, I'd like to start my actual presentation. So the first thing that I would like to talk in general is, the densification that can be achieved through hydrocyclone or physical selection, right? So here, what we are looking at on the screen is the control train versus the pilot train with hydrocyclone. And if you look at the control train, it suffers the seasonal variation in SVI. The SVIs can get as high as 250, and this has a negative consequence in terms of the capacity of the plant. If you look at the hydrocyclone train, the line on the bottom, you see that the SVIs are pretty low. They are consistently below 100, right? It ranges from like 60 to 100. And if you look at the settling velocities of the densified accumulated sludge hydrocyclone train, it is like twice as the control train. So they are settling very fast. So we know that hydrocyclones can, with improving settlability can increase the capacity of the plant. And this is what is understood.
Pushkar, we are
But
suffering some audio difficulties.
idea that I want to explore with my presentation today is, can we decrease
Pushkar,
overall activity of the system
Pushkar, can you hear us?
so that it already show and stories collecting. Is it better now, or?
Yes, that was wonderful.
Yes, hear me.
Please try again.
I think
We have lost all audio at this point.
you guys. Can you hear me? Hello?
Yes, now. Yes, we hear you better now.
Hello?
Pushkar, we have lost all audio.
Josh, if we can't fix this quickly, maybe we should move on to the next speaker and then have Pushkar join again at the end.
Okay. A few more seconds. All right. No doubt Pushkar's contribution was riveting and essential to our storyline. But we are going to move on to the next presentation, which is going to be delivered by Bruce Johnson of Jacobs, who's going to describe mobile biofilms. Pushkar, please pause your sharing so that we might move to Bruce, and we'll circle back to your presentation after Keith presents.
You see my screen, Josh?
Can you hear me?
I cannot. I still see Pushkar's. Pushkar, please stop sharing for the time being, and we will circle back to you at the end.
Perfect.
Okay, you're live, Bruce. Please continue.
Okay. Thanks, everyone, for technical difficulties on Wi-Fi there. But again, I'd like to thank everyone for participating in this. And I'm going to present a
I'm
case
not
study.
sharing anymore.
I'm going to present a case study on how mobile biofilm carriers can improve selector and settlability in the system. My co-authors on this are Tom Johnson with Jacobs and Jason Calhoun, now with Arcturix. I don't know how to say its new company. So with that, looking at new technology like we're talking about here, as Glenn said, selector technology has been around for quite a while, but the idea of using biofilms and ballasting to improve sellability is relatively new in our industry. And so any new technology is going to be characterized by these innovators and early adopters, and people can start taking these on. So when you're in that early adopter and innovator category, you want to make sure you've got your I's dotted and T's crossed in there to ensure that your investment is going to pay off in the long time. And then in our industry, as everybody knows, we're a pretty conservative industry usually. And there's a lot of different groups that are part of that. So partnering to develop the best approach is an important piece of it. So back in the late 2010s or 2000s, RF wastewater was created with a new technology, mobile organic biofilms. And what this is it takes the plant stems from the canaf, the hibiscus cannabis. Lots of jokes there around cannabis family, but it is not mellowing. But it is the ground up stems of that, about a 0.5 millimeter particle that is used and added to a mixed liquor system to grow a biofilm and also ballast the sludge that's then joined. Very similar and almost identical to how AGS works. So in early 2010, we looked at the development of this technology and partnered with Nuvoda and found that it had some potential. And so we started out with a measured approach to evaluating it, including the bench scale testing, developing the simulator, going on to full-scale equipment, and then actually full-scale operational testing of the bioreactor. Now, the bench scale testing at first was pretty straightforward. We did bench scale SBR testing of MOB versus conventional activated sludge. That's what CAS is. And we operated over quite a long time, and and had a pretty small fill in the MOB system, only 1.2% versus kind of conventional IFES where people are thinking 40, 50, even 60%. And what we found in that testing is that the MOB system did settle approximately 24% better. So this is a good sign. That allowed us to move on to continuous flow testing, where we compared MOB versus conventional activated sludge and IFES. SRT, suspended growth SRT, that's important, as Josh has been pointing out in the chat, was only 3 days for these systems. And as expected, CAS didn't nitrify in the system, but IFES and MOB had similar effluent performance. But MOB was found to actually settle quite a bit better than either of those other two systems. And as we know in bench scale systems, as shown below there, these things are notoriously difficult on operating and settling. So now we had a system that was in place, appeared to work, had better performance. We had some data about that performance. So we actually partnered with Dina Mita to develop a mobile carrier model. Now, a lot of people don't realize that most of the current biofilm models and systems confines the biofilm to the CSTR that it's in. The mobile carrier allows that biofilm to transfer between different environmental conditions. And by doing that, we were able to then scale this up to full size and understand what the various impacts of this were. So the next step was the full scale, making sure the equipment worked. As Pusker was going to talk about, and hopefully will still, there are a number of ways of getting those physical selectors in place to remove those granules, or in our case, the biofilm canaf particles. And here we tested a drum screen to do that, and worked very well there. And but it was also really good at capturing trash. And so we did find that it was important to get good influence screening to the plant at 6 millimeter in there. So equipment works now. We found that out, and now it was the time for full-scale testing of this. And what we did is we piloted this at the Mebane, North Carolina water reclamation plant, 2.5 MGD facility, 9,400 cubic meters per day. Had a fairly stringent nitrogen limit, less than 5 milligrams, well, 5.3 milligrams per liter TN, and also good total phosphorus. And how this plant works is they have surface aerators in these two bioreactors, and they operate them in pairs, but they get their nutrient removal by turning them on and off to get those anoxic aerobic type conditions in those reactors as a part of this. And so this, as Josh referred to, there's actually three primary ways that we can retain those granules in the system. One, you can screen everything, which is an expensive screen. Two, you can screen everything and add RAS into it, this mode 2. But the mode 3 is what we were doing, where we were only screening the WAS, the waste activated sludge, and then returning the biofilm back to the RAS, so that we had not infinite, but a very long SRT in the granules themselves, and a short SRT in the suspended phase. Now with that, you can see the results that we've got here, where the sludge age dropped from about 11 days prior to MOB down to 8 to 8.5 days during the pilot test. And then you can also see that, that prior to this testing, the SVI was around 175. And after the testing, other than a little upset in there, we had significantly lower SVIs down in the 125 range when we were doing that. So it showed that this ballasting type selector effect actually was pretty effective at reducing the SVIs in the system. And effluent performance was just as good, pretty much. They actually operate their aerators to achieve a certain ammonia out. So you can see that on the left-hand graph that they did not really see a big change of that. In the right-hand graph, we had a little bit of a nitrate upset, you can see during the test, where they actually overloaded the system. But once they brought that second basin online, the nitrates went right back down to where they were hoping to get them as part of that. So the conclusions from this was this partnership between Novota and us of using this methodical and defined steps allowed this proven development, a lot of confidence in this novel biofilm and settleability improvement. This process model allowed us to scale it up to whatever size we needed to. And now MOB is, mobile biofilms have become a commonly evaluated intensification technology that has both biofilm and settleability benefits in bioreactor systems. This is international. We've got places in Canada, UK, and even Australia that are considering this. And it's also a growing technology. There are other vendors that are getting into this market now. And it's not just a single place, which is good for us all to have that type of competition. With that, I'd like to thank everyone and look forward to answering your questions.
Thanks, Bruce. Thanks for a riveting presentation about mobile biofilms. Next, we need to decide whether we're going to bring Pusker back to describe physical selectors, which I think is important because it offers context for the remaining speakers. So I think we should try to reintroduce our friend Pusker Reshmi.
All right.
Wonderful.
So,
now, panelists, please turn off your video so we can give him as much bandwidth as possible.
Yeah, so also I'll not be on video just to save some bandwidth. I apologize for the inconvenience. I'm hoping like everything is good. So let's start. So with this, what we'd like to talk about today in this presentation is a couple of case studies that we have done over the years. And the first one that I would like to talk about is Pueblo, Colorado. And here we learned about like hydrocyclone implementation and how it can offer, physical selection that can decouple the SRTs, right? So when you have a hydrocyclone, what ends up happening is that you have basically two SRTs of a system, a floc SRT and a granule SRT, right? And if you look at them carefully, what you'll see is that the granule SRT, which is shown on the left here, is going to be much higher than the floc SRT. And this is kind of makes sense because the densified particles, they end up in the underflow of the hydrocyclone and they experience a longer SRT that way. But the most interesting thing here is, what happens to the things that we want in terms of the biology, right? Like, for example, specific nitrification rates. And we did some of the specific nitrification rate measurements in the underflow and the overflow of hydrocyclone. And what we saw was that the underflow had much, higher specific nitrification rate compared to overflow. It was actually, 40% higher in the underflow, right? So this tells us that perhaps not only the granules are being retained, the microorganisms that we care about when it comes to BNR, especially nitrification, nitrifiers, they are also retained in the underflow, selectively retained in the underflow, right? So if you want to learn more about, some of the results that I'll be presenting here from Pueblo, you can, reference or you can read the water research publication from 2022. And so this is pretty interesting observation, right? So, and the other thing that we did recently, this was a more recent kind of a, study that we are doing as part of Water Research Foundation 5083 project, where we looked at, systems which are operating in low DO conditions and what sort of nitrification rates that we can get. And when we lined all the information from different plants, Pueblo sort of like stands out. So if you look at this box, Pueblo nitrification rates are much higher than nitrification rates from other plants, which are also operating in low DO conditions. So there is something about retention, selective retention of nitrifiers in the system that could be contributing to this high specific nitrification rate. The other interesting thing is, Pueblo does have this automated aeration control. And when you are doing automated aeration control, like ammonia-based aeration control or AVN, ammonia versus NOx aeration control, you do not select a DO set point. You select your target, and the DO is dynamic. And based on the specific nitrification rates that is available for the nitrifiers, the DO set point can go very, very low. And as I show here on the right, the DO distribution, the 50th percentile DO is less than 0.3 milligram per liter, right? So it's, the idea here is you're getting densification, but at the same time, the oxygen affinity for AOBs are not suffering. This is a very wonderful place to be when you are trying to optimize both PNR and densification. The other thing that we did is we looked at the specific nitrification rate at high DO and compared that with a low DO. These are done in a batch experiment. And when we did that, even at 0.2 milligram per liter DO, the specific nitrification rates didn't go down significantly. Right, there was some decline, but it's not very low. So this tells us that low DO and densification can be compatible, and this is a bigger part of the story where you can get intensification out of these systems, both in terms of SVI improvement, settling improvement, but also from a BNR perspective. And if we look closely at what happens with hydrocyclone, the particle distribution in the underflow of the hydrocyclone, which gets retained, and then on the overflow, what you'll see is that the particle distribution looks completely different for these fractions, right? So if you, the figure on the left here is the overflow particle size distribution. And we are looking at 10th percentile, 50th percentile, and 90th percentile particles. And essentially what's happening, at a high level is that underflow is capturing particles that are more than 150 microns, and overflow is predominantly, particles that is less than 150 microns, right? So most of the big particles are being retained in the underflow. So with this retention of granules and large particles, what ends up happening is you tend to decouple the SRTs, and the decoupling of SRT and how large your aerobic SRT is for the granules mostly depends on the particle size, it seems like. So the larger the particles, the bigger the decoupling of SRT that you can expect. So if you look at this, plot with, the floc SRT remaining kind of a very close to 5 days constantly throughout this study, while the aerobic SRT for the granules fluctuating and getting as high as like 35 days for the system. So the question is, do you need this like massive uncoupling of SRT and large particles, right? And to answer that, we've been looking at some more experiments. And here, what we are looking at is, different rates for different particle sizes. And the question that we are trying to answer is, are large granules better, right? So if you look at the specific nitrification rate on the table on the top here, you see that, the nitrification rates for particle less than 200 micron is high, and they go down as the particle size increases. But for specific P uptake rates, it increases for the particles which are between 200 to 600, then it starts to decline again a little bit. So the idea here is, particles which are less than 200 microns may be good from a nitrification perspective, and from a BioB perspective, particle size between 200 to 600 micron could be better, right? But more than 600 micron particles are not necessary from a BNR perspective. So to dig this a little bit more deeper, we did another round of this testing just to dial in what is the right fraction of particles. And if you look at the results here, we have chosen our different categories of particles, less than 100 micron, 100 to 200 micron, and more than 200 microns. And if you look at this closely, you can see that a specific nitrification rate is the highest for particles between 100 to 200 microns. And if you look at the P uptake rates, it is also quite high. It's not, significantly less than for particles less than 200 microns. So this seems to be a pretty good spot when it comes to particle size. And if you look at the picture below, for the 100 to 200 micron, you can see that these do look like granules. They behave like granules. So in terms of settleability, they are going to perform really well. They're going to settle fast, but at the same time, they will give you the benefits of retaining, nitrifiers and PAOs in your system. So it seems like 150 to 300 micron is a sweet spot of granule size for these systems. So to wrap this up, to get back to the final thoughts here, it seems like if we can finely tune biological and physical selection, we can help extend plants' capacity so that we can lower the SRTs. But at the same time, it's very important that we select for right particle size that can retain BNR organisms. That is more important than the granule SRT alone. You can have a very large granule SRT, but that doesn't mean that you have active fraction. And the active fraction of nitrifiers and PAOs are critical in realizing this capacity savings. So those are some of the thoughts that I have that I wanted to share, and look forward to the next presentation here.
Thanks, Pushkar. You came through crystal clear. Fine
Thank
recovery. You also have direct questions in the chat that cropped up during your presentation. I encourage you to please review them and respond. In the meanwhile, we'll move on to our next speaker. Clement Roche is with Suez, and will describe some facets of utilizing hydrocyclones as physical selectors with biological selection to accumulate granules. Clement?
Thank you, George. Can you see my screen, hear me well?
Yes, I can. It looks quite good. Thank you.
Okay, perfect. So my talk will be speaking about granules and hydrocyclone selectors with two full-scale studies in France, one located in Dijon, another one in Chevigny wastewater treatment plants. Both of these plants had H2O configuration. So the first one in Dijon was not featuring any primary treatment upfront, whereas the Chevigny wastewater treatment plant was having a primary treatment upfront in the biology. And both of this line was having anaerobic compartments. The big difference between these two cases was that the first plant Dijon was made of 3 biological stage selections, so contact followed by 2 dedicated anaerobic zone, whereas the second one only features a unique volume for the anaerobic zone, which was inducing a bit less of the feast famine conditions. Both of the plants were equipped with hydrocyclone selective wasting hydrocyclone batteries installed on the WAS streams. And the good thing about these two plants was that we had very independent biological lines in terms of recirculation and WAS, which was useful to be able to compare the line in similar influent condition and temperature and operating conditions. So I will directly jump into the results of what we obtained. And first of all, I wanted to mention that the densified biomass that we obtained was a mixture of different elements. First of all, yeah, somebody speaking behind. It was a mixture of well-defined flocs, as you can see on the top pictures, which is macroscopic pictures of a petri dish into which we poured some sludge. You could see that the flocs are very much well defined in the densified line, whereas the control cast has got much more fluffy biomass. The second fraction of this biological sludge is obviously the granules, which you can see appearing on the bottom pictures. But also, we could spot, at least in Dijon, some organic debris coated with biofilm, which could be viewed as naturally forming mobile biofilm. Of course, the debris coming from the wastewater, when you don't have a primary upfront, could accumulate within the system and act as a ballast and also a core for biofilm to develop on it. And the last but not least information about this, let's say, a mixed hybrid biomass is that we had almost no filament within this sludge. So the filamentous bacteria were repressed and get out of the system through the action of the hydrocyclone. And I like to believe that the hydrocyclone has 2 distinct effects on the biomass. So the biomass, which is constituted of this all different elements that you can see in picture in the feed side of the cyclone, are separated by gravimetry. The light sludge containing the filaments, weak flocs and pin flocs, is expelled at the overflow, whereas the dense fractions, including the granules and aggregates, are located downwards. And the first effect, which is the selective purging of the filaments, has an immediate effect on the biomass. As soon as you press the button, these elements are purged out of the system, and this purging is faster or works better when you apply a short SRT, because you don't let the chance for these elements to grow within the biology and you suppress them directly. Whereas the second effect, which is the selective retention of granule, is got a longer temporality, because the granule can only be retained if they are already present, and therefore their presence owes more to the combination of the biological selection, which was previously presented by Glenn, in place with the combination of the physical retention of those elements formatted by the cyclones or the physical selector in place. And so how does this translate into results in terms of setability? Well, the first effect, which is the retention of filament, in Dijon could be seen with a change of the seasonability. Previously, the installation of the hydrocyclones, you could see that bulking was seasonally occurring with recurrence every year of these bad SVIs. Whereas the experimental line in green just did cut straight and flat through the first ring and the second spring showing that the particle morphology did not much change. The difference between the 2 years, of course, is the appearance of granule, which could not arrive on the first year because of the, let's say, rather diluted influence we had in this plant that did not promote the growth of granules in the biological selector. So this is very important and has got some engineering significance, because the fact that we don't have any more fluctuability of SVI can provide for engineering practice and designs a stable SVI hypothesis to design more aggressively the clarifiers and the plants, because we can secure that the SVI is no longer fluctuating throughout the year. On the second plant, Chevigny, we learned some other things. And the thing we mainly retain from that experiment is that an hydrocyclone has got a similar effect on the biomass and the filament repression than a chlorination does. On this plant, of course, there was recurrent bulking, and the operator was dosing some chlorine to maintain the sludge in good conditions. And after the startup of the hydrocyclones, we decided to still dose the chlorine onto the reference line, whereas not to dose anything on the cyclone line. And we could see that at the beginning, the two SVI trends were exactly the same when the reference line was chlorinated, while the other one was just having the hydrocyclone selection. And of course, this plant had similar setup and location than the previous one. The first period corresponds just to the repression of filaments, and it only starts to granulate when there is less dilution water incoming to the plant. And from that point on, you could see that the two SVIs really differs in between the lines. In terms now of the second effect, the retention of big particles, this is the disjoint results. You could see at the steady state that the granulated fraction of the test line was around 50 to 60% in mass. And you could see on this graph the repartition curves of the granulometric size of the particle, with the hydrocyclone enabling to change the let's say the 50 percentile median diameter and increase it almost as double, rendering half of the particle more than 200 microns. But not only that, it is important to note also that the granules are not such big with an hydrocyclone, because the shear stress in the cyclone actually avoid the granule to grow too big, because they could break up every time they go through the cyclone. So that was for the change of morphology in between the two lines. And in Chevigny also, we had a similar amount of granule in the end at the steady state, with a granulated fraction in mass around 50%. But what was very interesting during that experiment is that during the course of the trials, we had an issue on one of the clarifier, and one of the scraper bridges of the clarifier of the control line had to be repaired. And after this reparation, we transferred some of the densified biomass containing granule into the control line, which therefore increased its granulated inventory. And we could see from that point, after this transfer, the difference in behavior, with the control line with no hydrocyclone showing a gradual exponential decrease of the granule concentration, whereas the other line exploited or operated in the same condition just did maintain and increase a little bit more the granulated inventory. And so this second effect shows how the decoupling of SRTs is actually happening between the two morphological part of the biomass, which are acting differently and staying at different times in the system. With that ends my talk, and I would like to thank all my colleagues in Suez that help in providing and measuring all this data, and to bring up to you this interesting conclusion. If you have any question, please go in the chat.
Thanks, Clement. Wonderful presentation. Clement, you have some direct questions in the chat. Like Puskara, I encourage you to review it and respond, please. In the meanwhile, we're going to transition to our final speaker, Keith Sears of AECOM. Now, this presentation is special because it really highlights the role of biological and physical selection, in this case, for forming and retaining granules. Keith?
Here we go, Josh. Just trying to see if I can. Is it full screen, Josh? From the beginning. How is that? Is that okay, Josh? Can you hear me? Yep. All right. Well, you know what they say, if you're not first, you're last. So I'm happy to be last here today, and thank you for joining everyone. I wanted to talk to you a little bit about what we've been doing at Penticton and try and get some of the information just disseminated out into our community to let you know, when you look at all these presentations in aggregate, you really start to hear a message and trends. So we're hoping we can contribute to that body of knowledge. So first of all, I'd like to thank the operations staff out at Penticton. They've been absolutely wonderful and outstanding. And Sadir Murphy over at New Hub, who's been helping us along this adventure. So let's get to it. What is Penticton? Well, Penticton was one of the first BNR facilities in North America. I think it was the third, designed in the early 1990s. It was configured as a modified UCT process back then, but recently the plant converted it to a step feed BNR configuration. Reason they did that was there's just becoming a better understanding of the importance of managing carbon in these BNR plants. So that was the rationale there. So there's two independent trains, which is great because they're two sludges. It allows for side-by-side comparisons. The plant has this whole region has tight effluent limits. So TP of 0.2 milligram per liter, TN of less than 6 milligram per liter, and they don't use chemicals at this plant to meet these limits. So here's the flow sheet of the plant. You can see zones 1 and 2 are the anaerobic zones. Zones 3, 4, 5, and 6 are the anoxic zones. And zones 7 through 11 are the aerobic zones. Typically, they operate with zones 10 and 11 off, and they're able to just bypass to the mixed liquor channel from zone 9. They only use zones 10 and 11 when they take a train out of service. And what they do at these plants here is they surface waste from the mixed liquor channel, which inherently gives them some selective wasting before we even start. But what's common in this part of the world is the use of primary sludge thickeners or fermenters. And you can see here what comes out of the primary sludge fermenter, the fermentate. It's very high in VFAs. As Mari said in her earlier presentation, those soluble biodegradable CODs and VFAs are very important to drive that feast. So you can actually compare what we see in the fermentate. We get about twice as many VFAs as we do in the primary effluent. So how the plant currently operates is they operate it in what we call, or is commonly called, the S2 EBPR mode, where 100% of the primary effluent is bypassing the anaerobic zone, and it's only the VFAs that go into that anaerobic zone to drive that P release. So we've been at this for a little bit now. We started off in May 2018, and what we thought is, well, we were short on cash too. So we just thought, let's make a primary or a lamella plate clarifier and install it in the WAS chamber. So that's what we did. And what that lamella plate clarifier did is it allowed the heavy solids to settle, and then we wasted off the top the lighter flocs. And it worked well, but it only worked well in summer. That was the problem. When wintertime came along, we saw the results deteriorate. So we tried that for about a year and a half, and we got lucky. Santa brought us some hydrocyclones for Christmas in December 2019, and we installed the hydrocyclones, but unfortunately that was also when COVID hit. So we had limited opportunity to get into the plant and visit the plant. There was all sorts of new restrictions. So again, we saw good results in summer, but then in the winter, the granulation started to decline. So really what we wanted to do then is take a step back and focus on the biology part of it. And because it made sense, something's happening in wintertime, so let's get a handle on the biology. So we developed a new strategy last year. What we did here's our strategy, just kind of pictorially. So on the right-hand side, you see the control train, and there's a hesitancy in the full-scale plant to change too much altogether because we do have to meet permit limits. So we kept the control train always the same. 100% of the PE going to the anoxic zones, and really that helps us with the TN. But we did turn on the last two zones as a low DO zones, 10 and 11 there. And what that was thought to do was just give us a little bit more famine conditions. On the AGS train, what we did is we diverted 70% of the PE, primary effluent, to the front of the zone to give us more carbon. We decided to cycle the mixers on and off, again, increase that fermentation. So 15 minutes on, 2 hours off. And we redirected the heavy particles that were coming out of the cyclone, we redirected them right to exactly where the VFA supernatant was coming in to really give them the exposure to the VFAs. So what happened? Well, you can see at the start of the gray box. So the plant was just undergoing some operational changes, some work at the plant. We put the cyclones online right at the start of the gray, and we immediately saw both trains, the SVIs drop as things came into equilibrium. But for the first winter in 4 winters since we started this thing, we were able to keep the SVIs at around 75 or lower through the winter. So we had never been able to do that before. And then in the control train, as the common kind of theme was, we started to lose SVIs as things got colder and colder and colder. So we were about half the SVI in our hydrocyclone train. But the unfortunate part was we started to lose phosphorus removal near the end of the winter. What was happening is we started to get a buildup of nitrates coming back in the RAS. Those nitrates in the RAS started to contaminate the anaerobic zone, and we just weren't getting the P release that we used to see. So because, again, this is a permitted plant, what we did right away is we put the 100% PE back to the anoxic zone. That allowed us to get those nitrates back under control. But then what we saw when we operated in that mode is, again, the SVI started to climb. So once we got the P under control, the SVIs climbed, we decided, let's go back to where we were again, and let's see what we could improve. So we moved also the internal mixed liquor recycle line to zone 4. So it gave us a little bit of a longer anaerobic zone. So even though we're adding more carbon here, we were able to keep the P release going because we had a slightly longer anaerobic zone, and we saw the SVIs drop dramatically again. But what the surprising part here was, even though we were putting more carbon up to the front of the plant and less for denite in the anoxic zones, we actually saw denite, an increased denitrification in our AGS train. And here you can see that here. The nitrate coming out of zones 10 and 11 was basically less than 0.2 milligram per liter, while in the control train, we saw nitrates of around 2.5 to 3 milligrams per liter. So because of the granules, we were getting more carbon storage, and we were using that carbon storage along with things like particulate COD hydrolysis and endogenous carbon release. We were really getting a lot more denite in the AGS train, which was really helping us for everything. It was helping us for phosphorus removal. It was helping us meet our TN limits. So the plant right now is putting out TN less than 3 milligrams per liter. much below their limit of 6. So what's the message in summary? For us, carbon management is key. If we just couldn't put selective wasting on this plant and get AGS to work or densification to work throughout the entire year, especially in cold conditions. So for us, getting the biology right, first of all, was key. And part of that was the carbon management, putting the carbon where it's needed most. So by doing that, for the first time in 4 winters, we were able to get success down to 10 degrees C, and we've never seen low SVIs like this before at the plant. We saw a significant TN removal in the last stage. Again, we attribute that to the carbon storage and some particulate COD hydrolysis in that last stage. And we're sending our particle counts out to Rudy over in Denver, and he's been doing our analysis for us, and we're getting some really good granulation in the last year. So greater than 30% particles, greater than 200. Our last testing actually showed 42% particles greater than 200 microns. So things are looking positive for us, and we're happy to share some of the success with a broader audience just to get that message out there. So thank you for listening, everyone. Happy to take any questions.
Thanks, Keith. Thanks, everyone. Of course, we have worked very hard together for quite some time to bring this material to you all today. This is all of our first chance to see show together, and notwithstanding some technical difficulties, it was a pleasant show. So thank you very much to all the presenters. Thank you very much, Rob and the IWA Biofilms Specialty Group. Now we have a period for discussion. Granted, it is nowhere near the 40 minutes that we had anticipated making available, but a very active chat has allowed the presenters and myself to address some of the questions. Are there specific questions or discussion topics for the group or specific presenters? I am asking you, Jackie, especially.
Hi, Josh. There was one question, I think it was missed to Bruce, but I'm pretty sure you can answer it too. It's from Anand Patel. Since CNAF is organic, does it in any way act as a carbon source for the organisms growing on it? Since it is lignocellulosic, I would think it will very slowly biodegrades, if it biodegrades at all.
Good question. I recall that Bruce did respond. I will echo his response in saying that there, once the CNAF has been added to a system, in none of the operational mobile organic biofilm systems that exist, there's not been a deterioration in performance observed. And there is no evidence that the material serves in any way as an electron donor or substrate transformations. What we know now.
Okay, thank you. Okay, I think we have more questions coming in. From Ziwu Wang. Hi, Glenn. If nitrifying granules do not store carbon, how should we explain the feast-famine role in nitrifying granulation?
Because it's not the nitrifiers that create granulation, it's heterotrophs. And nitrifiers are a very small fraction of the population. You have to have heterotrophs to have granules.
Mari, is there a specific type of heterotroph that is important for granulation?
Well, you need slow-growing organisms to really form smooth granules. And there are specific types that you, like species that does it, accumulabacter type. So yes,
Are
there
PAOs
are specific
important?
PAOs, GAOs, but you actually don't necessarily need PAOs. They can just be storage formers without phosphate removal capacity. Some plants do not need phosphate removal. And then glycogen accumulating organisms are fine. They, by the way, also denitrify. So if phosphate removal isn't the goal, GAOs are fine. I guess the simple answer is yes, there are specific types of organisms required for granule formation, and these are not the canonical heterotrophs that have no storage capacities, but those that do have storage capacities.
I think that the nitrifiers accumulate inside granules in mobile biofilms because they have a maximum specific biomass growth rate that is in the neighborhood of the carbon-storing heterotrophic bacteria that are essential to granule formation. Thanks, Glenn. I'm reviewing the questions.
I may answer this one, Josh, about the study measuring the airflow per square meter and the turbulence of aeration in basins, a factor in the densification. Well, I don't think so, because we've been able, and I think I'm not the only case, in which we used some aeration control based on ammonia, which tend to reduce a lot the aeration intensity and minimize the DO working. And this never actually forbid to create granules. On the contrary, my conclusion on the site is that lowering the aeration helps to better denitrify, and better denitrification makes your returns from the RAS, from the clarifier, containing less oxygen and nitrates, which brings a better anaerobic condition into the selector, which helps to develop the storage organism. So my conclusion would be, rather than air flow per square meter is not a criteria in continuous flow granulation to get the granules for me.
Thank you. I thought to respond several times to more than one post pertaining to greenhouse gas emissions associated with this form of intensification, especially nitrous oxide. I wonder, do any of you, the panelists, have ideas about the potential for these systems to produce more nitrous oxide than a conventional activated sludge process, or less?
I do. We have a study showing that aerobic granular sludge doesn't necessarily produce more nitrous oxide than conventional sludge. There is right now a study that will be published very soon. It's in review, where we look at the impact of granule size on nitrous oxide emissions. And there's some lessons to be learned how to manage granule fractions if the question is to reduce nitrous oxide emissions. So in total, I guess it's the same. And the good news is, if we manage sludge fractions, we can make it even better.
I agree. think there's a great deal of potential to make it better. I can't speak about granules, but in context of IWA Biofilms, there is real potential to reduce the electron acceptor, the dissolved oxygen requirement, and that is principally done through other types of microorganisms that oxidize ammonium. We should no longer think of this in terms of ammonia oxidizing bacteria and nitrite oxidizing bacteria. Ammonia oxidizing archaea, comomox, maybe even animox have a role to play. Folks, we are reaching the end of our allocated time. And I want to invite the panelists to offer any final comments before we communicate to the audience where they may find this recording. Anyone care to comment?
Can I take one question, Josh? Can I take one question? I think it's a pretty important one. Yeah, so the question is around like why, we were able to maintain like high oxygen affinity of nitrifiers on the granules. It's a very important observation, I think. It allows us to do efficient BNR and so forth. So I think the idea here is nitrifiers are like, using granules that are already present. So you form the granules by biological selection. Nitrifiers come in, they become part of the granules because granules are experiencing long SRT, which they need to survive. But at the same time, there is some level of adaptation that is happening. And when we looked at these, systems, we are seeing like comomox dominating the population of nitrifiers pretty much, right? So it's a combination of factors, I believe, that is helping sustain like high specific nitrification rates. And it's a synergistic relationship between the physical selection, biological selection, and adaptation of microorganisms, which is allowing this efficient pathway for BNR. So again, to pin down like every single mechanism is difficult, but the synergy is pretty obvious, I feel like, in terms of what we are seeing.
Pushkar, I'd like to add to that, the DO sensitivity that we see in our systems have very little to do with the actual sensitivity of nitrifiers to oxygen concentration. It has everything to do with first diffusion, but especially competition between the nitrifiers and heterotrophs for oxygen. To the extent that we limit the presence of fast-growing heterotrophs, which consume oxygen fast, and encourage and develop a population of slower-growing heterotrophs that use oxygen slower, right there, that relieves that competition and makes the overall performance of the system, the apparent behavior of the system, less for nitrifiers, much less sensitive to DO. So people think that nitrifiers are so sensitive to DO. They are not. It is really in our systems, it's competition and diffusion that determines the sensitivity, and competition in particular for oxygen between heterotrophs and the nitrifiers.
Yeah, just to add to that, I think we are taking too much of time. But the systems that do pretty well in terms of nitrification, specific nitrification rates, they also tend to do quite well with SND, simultaneous nitrification, denitrification. And the reason it seems like is the same storage that we are talking about, which is necessary for densification, also is quite helpful in generating like denitrification in the aerobic zone, especially with low DO conditions, right? So it's the same carbon that gives the density to the organisms. That same carbon also provides you substrate for denitrification. And so you have this win-win situation, right? So the carbon is giving density to the particles, it's settling well. It's also providing, you're avoiding that aerobic oxidation of carbon in the aerobic zone, which, what Glenn was referring to, right? So you are not doing aerobic oxidation of carbon. You're using it like for denitrification. So it's a win-win kind of a situation. So everybody's happy, right? I think there's a lot to explore here, but it seems like everything is converging and giving us like efficient BNR systems.
Thank you, Pushkar, and thank you, Glenn. We want to be respectful of everyone's time. We appreciate your attendance. Special thanks to the speakers. Special thanks to Rob. Rob, I ask that you close this webinar, and I think people will be interested in knowing where they can find the recording.
Again, just to follow up, Josh, thanks so much for taking the lead on putting together this webinar. Thanks to the panelists for all their time and effort in presenting this, and thanks to the audience for participating, some maybe at really odd times, given the international scope. We will send a link to all the participants where they can find the recording. It might take a few days, but you'll have the link. We'll also make it available on the IWA Biofilms IWA Connect site. If you're not a member of IWA, you might want to consider joining because there's a lot of great materials that they can provide. So with that, thanks to everyone, and I think we're done. Josh, are we done?
Yes, signing off. Have a great day, everyone. Take care of yourselves, and bye-bye.
Thank you. Bye.